Hi, my name is Aimen Zerroug, and I'm going to talk to you about our work on self-supervised learning for skeleton-based action recognition. Self-supervised learning is a method for pre-training neural networks on unlabeled data in order to improve their performance on downstream tasks. It has been widely adopted in machine learning and especially in computer vision. Certain models pre-trained with self-supervision can reach or even exceed the accuracy of models trained with label supervision. In this paper, we explore prior work on self-supervision techniques for action recognition from skeleton sequences. Our main goal is to unite the objective functions used in the domain under a single taxonomy. In self-supervised learning, the model learns to represent inputs without label supervision. In auto-encoders, for example, the label is the input itself. The input is represented in a compressed latent space and reconstructed from the latent vector. In contrastive learning, the label is provided by transformations of the input. Representations of transformations of the same input are pulled together, while transformations of different inputs are pushed apart. Prior work on action recognition explores both approaches. Our taxonomy starts with these prior works and infers other missing objective functions. In the taxonomy, bottom-up objectives are computed over high-level representations and top-down objectives are computed over low-level representations. Objectives based on attraction maximize the similarity of an output to a specified label, while contrastive objectives additionally minimize its similarity to other labels. In practice, we follow prior work in the choice of an RNN as a backbone in the encoder and decoder. The query encoder is used to compute both the bottom-up attractive and contrastive objectives. The key encoder provides positive and negative keys used to compute the contrastive loss. Positive keys at one training step are stored in a dictionary and used as negative keys in future training steps. The query and key decoders are used in a similar way to compute the top-down objectives. For more details on the methods, I invite you to read the paper. Through systematic evaluations, we find many interesting conclusions, mainly that combining objective functions leads to an increase in performance. We also discover that the best performing combination of objective functions is bottom-up attractive, bottom-up contrastive, and top-down attractive, which led to competitive performance with state-of-the-art on several benchmarks. It also outperforms most RNN-based methods. We provide all details of the standard action recognition benchmarks in our paper. Finally, we evaluated the model's robustness to transformations. In the contrastive learning training process, the projection space is used to compute the contrastive loss, and it is trained to be invariant to the transformations applied to the input. In the plot to the right, the model is 100% robust to a transformation if the representation of the transformed input is the nearest neighbor of the representation of the raw input in the projection space. In this experiment, we find that for all degrees of the transformations, shear and rotate, the model with the highest action recognition performance is also the most robust to transformations. In conclusion, this work proposes a taxonomy that unites disparate approaches to self-supervised learning and tests this taxonomy in the context of skeleton-based action recognition. Our taxonomy shows the complementary benefits of the objective functions to the model's capacity at extracting semantic information and the model's robustness to the random transformations. Thank you for listening.